I suppose this discussion is a lot related with the previous one, and actually we found a less smart way to do the same things, but we were really focusing on the output. I think we will be looking into this Python things a lot because it will help what I'm gonna show. But essentially the problem we are gonna discuss is about the CLT design and how we have tried to use SOFiSTiK for improve our internal routine on the CLT design. CLT, it's a timber product, is an engineering timber product, very common now in Norway. It's a material of several timber boards glued together in two directions with a specific system that makes it very different from the other timber products on the market. I will go very fast on that. I will just present the company very quickly just to explain to you who we are, but I will go very quick because I want to talk more about the technical topic. We are an office focused on architectural projects, both in the timber and the building industry. We are present now in 3 places. We have an office in Oslo, one in Valencia, where we do most of our technical development. And then now, recently, we have an office in Athens, where we do some geotechnics. All the team, we met somehow before, and we worked together for many years in other companies, and now we are all together trying to deliver the best we can some high-end engineering. We are a small firm. We are in total now 35, and of course we do whatever it comes to be done. But we have seen ourselves more and more in some specific market because it's the place where it's easier for us to get the contract. So we do a lot of bridge design, especially complex steel bridges. And we have done recently a lot of CLT buildings because it's new things, there is very little knowledge. And also we have been asked to help people on beam fabrication models and direction sequencing, but direction sequencing is very complex. Our work, we use several FEM analysis model, we use Rhino and Grasshopper, and for the beam modeling, Tekla and Revit. I think the industry now is a lot more like Revit building, Tekla, bridges, but I think it's quite kind of interesting how both of them are working, trying to still segment to the others. No? So for example, I was very interested to your chart because Revit, do a bridge in Revit, now it's, you have to believe it. No? And yeah. So, yeah, our special company, steel bridges, timber construction, complex geometry. I will just show you, this was a very long portfolio, just some timber construction, just to give you a hint why we are entered this market and why I think it's technically interesting what we are going to present. Because the timber industry, especially where has been born, that is Austria and Switzerland, it's a very simple and like box building driven. So actually most of the engineering company that are dealing with CLT, they were doing a lot of hand calculation because the building were straightforward. There was no need of FEM modeling. There are no FEM programs think for making CLT because it was very easy. But then these things exploded for the sustainability and CO2 impact that we have seen. And then the architects started to love it. And the architects, unfortunately, I think they're very bold on selling bright ideas, no? But they get not so interested to the challenges that are behind that. And so we are seeing a lot of very long span, crazy supported structures that you look at them and you say, maybe if it's concrete, it's core connected, maybe it works. But they propose it in CLT. And then we have to engineering. So you will see, for example, this is a being built in Stavanger, this staircase. It looks cool, but it's double curvature and it's one piece. And it costs one apartment in Oslo, central Oslo, more or less, each piece of this. You know? And has been engineered in Germany and delivered to Norway. Timber connection. Very nice, very sustainable, but of course you have to start to take in account friction, contacts. Yeah. Another project, again, with same architect, very large portal frames. Timber is not meant to be continuous, so portal frames in timber, it's tough. This is Drammen, high rise in CLT. Again, possible, but when you have a core, you will never have one core like in concrete that is continuous bottom to top. So you will have always a panelization, no matter how much you push the boundary of production. You will not be able to transport more than 20 meters from Austria to Norway. And then even a little bit smaller scale, a lot of we are doing a lot of barnehage, sports hall and things like that. Even in this small one, the architect starts to remove columns everywhere, walls everywhere, and you end up with something that looks easy, but actually is not from a calculation point of view. Yeah, up to, this is in Berlin, is a competition, and it's gonna be the highest timber building in the world. I hope it will not go further with this concept, but at the moment, yeah, and this is the, in my opinion, like the high hand of what we have been asked to do. This is a toilet in Norway. Probably the most expensive toilet in whole Norway, by the way. These trees here are real trees that we have monitored 2 years in the wood. Pick it up. This is the nice one. I love this one. And they've been extracted with the roots from the wood. Take 1 year in drying, then cut. And if you see, the same tree is positioned one times with the root, half of the tree is positioned with the root down and one with the root up, and disposed in a circle. And then what you get a sort of natural column, void in the middle, so you can put a toilet. And this thing is supporting a massive concrete things that has been realized by filling the entire area with sand, and with the architects supervising some guys digging in this organic shape that was actually, we had an NFC of this, but you can imagine how precise you can be like that. And then they casted over the sand way too hard, and then they remove the sand, and then you have this toilet. I don't know. Yeah, okay. You see here, this is one piece of. They produced it more just in case something went wrong. Yeah, you see that. But back to the technical things. What is this improved CLT design? I mean, the point of CLT has arisen in Norway for essentially for the topic of sustainability. No? So you can almost, it's probably one of the few materials that you can follow the C2C, cradle to cradle principle. You start with a tree, you enter a process where the tree is engineered to make the building. In the meantime, you have planted more smaller tree, and during the 100 years that your building will last, you ended up with dismantling the building, burn or reuse the timber, and start the cycle again. And during this cycle, essentially, you store either or you save the same CO2. No? So this is a fact we cannot really influence too much. So there is an industry that is very eager to use this material. The problem is that here in Norway, for example, there is a long tradition of standard bindingsverk and Trebjerkelag. Norwegian knows what this is, like construction based on stud walls. vertical, or a system of beams in the horizontal plane where you put then a spoon platte or any ply deck to make the floor, and you make your home, you make your relatively small to medium building. Now, if you translate this to a large building, the first things you discover is that the time is going up in a way that it's impossible for the contractor to perform the building in an economical way. No? So it's when it started the idea of having larger elements to be used on site, and these elements then will allow you to speed up the process. That's the only things. The drawback is that you use a lot more timber. That you have, instead of a series of beams every 400 with a thin layer of top plate, you start to have 300 millimeter thick timber things. So it's a lot of meters cube, so a lot of weight. They are heavier and they are more complex to design. So, by the way, CLT is one of the few materials that is not covered by the Eurocodes. So actually, at the moment, every one of us that work with CLT, we're working with no umbrella. I mean, there is the University of Graz in Austria that has produced a lot of documentation, very interesting. Most of the calculations we do are based on that, but there is no information about this material in the Eurocode, so you're on your own. And this is and I think this is interesting because, I mean, there is at the moment almost not any FEM software that has any design routine for CLT. So when we started, we developed our own system in Excel based on the formula from the University of Graz. But the biggest problem we had was that you have, as you all know, hundreds or thousands of shell elements. You have hundreds, thousands of combinations. You ended up with thousands of lines. You perform the check. In Excel is quite handy. And then what you do with 10,000 results, where some are all verified and some are, I don't know, 10% over the ratio. How you identify which element is failing for which combination, how it makes sense. So we ended up thinking to use SOFiSTiK, and I'll show you why we are now using SOFiSTiK. Before we were using SAP 2000, but we are more happy with SOFiSTiK, I have to say the truth. We post-process a little bit the data with MATLAB to order it for our Excel prepared routine, and then we get the results in Excel and we print it in MATLAB just for visualization. So the topic we were having before, to write back to SOFiSTiK, for us is very interesting because we would really like to see these things closing in SOFiSTiK because it would be a lot better. But for the moment, we print in MATLAB. What we work with? We work with shared forces because these elements are 2D elements. So they are elements, just to give you an idea, the typical CLT element is from 80 millimeter to, I think the maximum now they're producing is 340 millimeter thick. It comes in width that range from 1 meter to, I think the maximum I reach now are 3.5 meter width. And the length, in theory, every fabricator says to you that is almost whatever you want, because these things goes in a machine that press it after glue it. So essentially, you can extrude, in theory, as much as you want, but in reality, for physical reason that you have to transport someone else, I think the longest they have produced is 30 meters, but more than that is very tough. No? So whatever building you have to split it in modules of, let's say, roughly 2-3 meters, thickness of 200 millimeter, and then length, yeah, ideally 10-15 meters, not more than that, if you want to transport it. So we have to model with shell, and that's a very bad thing because shell, you have a lot of, it's very complex to understand the behavior of shell with respect to a beam. Beam is moment, axial force, very easy. With shell, you have a very complex thing, and CLT has more complexity. I will show you in a sec. To make it happen, we have to export groups, combination, element, node, and then define joint connectivity, joint coordinates, and export everything in TXT. How we do that? Hopefully we will do it the same way you do in Python, but at the moment we use steady, we just essentially we print tables. And then we read the tables that we print. Why use Excel and why we cannot use other stuff? The problem is the material. No? The material, you see here how it looks like. You have boards of timber. By the way, one of the reasons of this is because the Austrian industry was having leftovers. Because when you cut a tree, you cut the tree, I don't know if you've seen it, but you have the middle curves, and then you start to split it, the circular one, to get the tables, and the premium one are the larger one. So it's the timber where you make a lot of money. And then more you go towards the edge of the circle, and the smaller is the table that you are able to cut out. And also the quality, is not that good. So before they were throwing that. And now instead, because essentially this is all covered, they glue together these lamellas that are relatively thin. They are 100 millimeter by 20, more or less. This is the typical ratio. And they attach it in two directions. So this goes in this direction, this one goes in this direction. The typical CLT has always 5 layers. This is the typical. So you get 5 in one direction, 2 in the other. So you get a pretty decent material that span in 2 ways. Of course, as a main span, one that is stronger, one is a little bit weaker. But it's actually nonlinear. So you see here the stress distribution. Because timber, when you are against the grain, has a modulo of elasticity of 12,000. When you go against the grain, it's 1,000. So it's 1 to 10. And also the stress capacity is the same ratio, 1 to 10 more or less. So the formula, the standard formula that everyone knows about steel, for example, are not valid. You cannot only do the M divided by W. Plus, the timber has to also account for the fact that it has a very large creep, and this is a very important topic for timber, so it has this come out. Plus, of course, you have the problems of buckling, like in steel or concrete, and things that are very pure to this material. So here you see the typical formulation for shear stresses. But if you think that the shear stresses is always, you can think in 2 ways. It's the vertical cut of a solid element, but the same vertical cut is also associated with movements of the compression part with respect to the tension part. So you have, it's the same thing that you notice in composite structure. You have tension steel member, a compressed concrete, and you have a shear in between that normally you take with studs. The same things happen here because you have 5 lamellas, and the lamellas are not, unfortunately, very few producers, almost none, glue this part. So they are glued on that surface, but not on that surface. So the lamella, when you apply the movements, it can roll like that. And this is called roller shear. And this effect is taken by the University of Graz with this formula. And you can calculate this shear that it doesn't exist in other type of things. More type of mechanism of rupture. All of them have to be checked. So conceptually, it's very easy because you have a bunch of formula. all these formula are based on results from a pure shell elastic analysis. So you take the F1,2, the F2,1, the M1,2, M2,1, and so on. You combine together with this formula, and you get stresses that you can compare with a stress limit. So it's very easy conceptually. The problem is that a lot of equation and a lot of shell and a lot of nodes. The other problems that we face with CLT is the stiffness. And as you know, in a building where you have hyperostatic situation, so it's not isostatic, the forces flow depending by the stiffness. So if you establish correctly the stiffness, then you have right result. If you establish the stiffness wrong, you get wrong results, and whatever you do, it's okay on paper, but it's not valid. So the problem of CLT is that it's orthotropic in the lamella, and is orthotropic because you have lamellas in two different directions. No? Until SOFiSTiK, we were calculating with our in-house software the stiffness, and then trick SAP 2000 with a different matrix to do their calculation. So the rigidity, the matrix of rigidity of the material CLT was input by us. Now in SOFiSTiK, we are trying to use the module that they have for layered material, and is giving good results. Here you see the matrix we were defining before. Now instead in SOFiSTiK, you create a special material. It's interesting to notice that if you have different thickness of element, you have to define different material. You know, before with a normal material, you define only the material, no matter the thickness. But with CLT, you have to define exactly this. And by the way, each producer, because of their line, has different lamella thickness and things. So even the same product, bought by two different ones, will have a slightly different definition and a slightly different stiffness. And that's a challenge for us, because sometimes we arrive earlier than the producer. We have tested you, so with our program we get 14.8 in this small example. You get 13.2. We are digging why, but I will let you know. If we found it, we'll let you know, but it's pretty accurate, I think. Now I have, before showing to you how we have applied this to a small example, I want to talk, because we are invited by SOFiSTiK, about some good stuff we have found in SOFiSTiK that has speed up our routine. So let's just very briefly talk. First, SOFiSTiK has this area element. So actually, we can let this program to mesh. But we can define each module of our construction as one single element, assign some properties, and copy and paste, and then we copy and paste the same properties along the building. This has been for us a very important help. The second thing is that by using wisely the axis X, then we can define, as I was showing, the material is orthotropic, so has different stiffness in two directions. So it's very easy to define with the axis which is the main direction of the CLT product. And this is also even more important when we do these kind of things that are very common on the industry, that when you have a large openings, to save money, they just put a lintels over, made of the same CLT. But then, because this element, instead of being an element, a vertical element where you want the three lamellas in the vertical one, because it's an element that's working bending, you want the three lamella horizontally, and this is a lot more effective, no?
So, and you can easily do that in SOFiSTiK by select the element and rotate the axis, and then you get the other type of panel. The most interesting for us, and the one that we are using more and checking more now, is that in previous modeling, we manually split each panels with a gap of 5 centimeters. In every single real splice, we had to make a cut of 5 centimeters, and then each node of the left part connect to the node of the right part with a spring. The reason behind that is that every time you fix timber to a timber, you use either a screw or a nail, and this nail has, according with Eurocode, actually this, has what is called slip modulus. The way that the screw works is that it's able to give you the resistance you're asking, I don't know, 3 kilonewton shear capacity of the nails, but this will happen with the nails deformating itself in a sort of S-shaped curve. So you get that by a sort of slip of one surface with respect to the other. And this slip seems stupid things, but really completely change the way of the forces are distributed along the element. I will show you a picture and you will understand it. So in the case of SOFiSTiK, what is the advantage is that we have these edges and we can define what we want to disconnect. Actually, it's pretty, I think it's well done in the sense that when you define the edge, you get another axis, and these data are referring to this axis. So when you say UX, you are implicitly saying that these two panels, they can slide in this direction one with respect to the other, and then by assign an axial spring, then you are connecting again, but you are connecting these 2 points with a spring that you don't have to model. I mean, it's a lot of time, effort reduced. The only things that I've noticed that you have to be careful, or at least we have tried to do, is that if I define the edge on this element on the left, on the next element on the right, I don't define nothing. Because if not, it works, but when you print the data, you have double data for the same nodes, and it's quite confusing for me, because you get the data that in theory is to be the same number, but you get the data for the node that is representing the connection to the shell 1, and to the same node the data of the shell 2, and I don't get how that works for me, but yeah. And of course you can do very easily with this fantastic auxiliary beam element. You can apply the support forces, the support restraints very easily. Now what allow you to do? It allow you to, for example, read, these are forces in the y direction. So when the wind is blowing this way, you see the slip of, you would expect that if you apply a load, then this force is constant, or it doesn't invert, but it invert because this panel rotate with respect to the other, because this connection here is not rigid. So when you apply the wind here, it's not receiving a compression, it's trying to rotate like this. And then you get compression forces, tension forces, and you get the same behavior on the edge. And this is extremely important to establish how many screws you have to connect the two elements. And you see here the behavior. This is from a book, so this is the theory. And you see how SOFiSTiK catch that, and actually how important is the edge elements, because you get larger forces on the edge. That is quite a typical behavior of these kind of things. And the other fantastic output we are using now, we don't know how to standardize that, but we are using a lot, is that in reality, what you will do in the final phases is that you have, for example, a tension forces here and a compression forces here, and you will place two type of different connection. One is called the hold down. It's like a bracket in steel that it's very high here and connected to the concrete, and a small one here for shear and compression. And you want to know what is the force that they have to take. Instead, here you have like distributed things. You know? And SOFiSTiK allow you to integrate this one and give you, with respect to the exact point where they integrate, they are doing the integration here, the total shear forces and the total tension forces and the total compression forces here. So with this number, this is the integration of this curve until a certain point, you can design your connection. We are quite new with all this. We were, as I said, working with SAP before, so I thought that was not nice to present you in a SOFiSTiK conference SAP results. So we apply just for this conference the infrastructure that we have now available for SOFiSTiK. We applied to a fake invented building. This is not, I just invented just to show you the possibility. You see, when you apply the wind, you can read how deformable is this building with respect to a corresponding concrete building, for example, and how important is this deformability, because it brings the loads in a completely different pattern with respect to other more standard construction materials. And when we apply the procedure, then we are able to post-process, do all the formula that I was showing before about stresses, and plot for each formula, or we have identified a group of formula. For example, we plot together axial and bending, we call D1, and we can plot it in real MATLAB things that allow us to rotate and go around and check the elements and see the interaction factor. So for example, this is axial bending in plane shear. So we can, for example, dig here and see why we are over 1, see the element, go back to the formula, see which combination it is relevant, is not. It's an effect of linear concentration of stress, or is relevant. You see here in plane shear again, transverse shear. And we did that already. We have planned to use the same strategy for a lot of other checks that we think SOFiSTiK either don't do or don't do the way that we want. And one is definitely joints. We have already started. So this is a real building. So here you see plotted in 3D each single connection device. So this can be, in this case, these are plates, but could be a screw, could be anywhere, anything. It's an object that is positioned in a certain point in the building that is represented to a spring in the SOFiSTiK model, and from what we extract the data in terms of forces, we check it according with the formula of the element itself, and we plot the results on MATLAB graph. And one thing that we have used a lot, this has been developed by a summer student, very bright. SOFiSTiK for beam element gives you the deflection. But a lot of time, especially in timber building, your beam is supported over, for example, another beam. And you are not interested to absolute deflection, because you are interested to the net deflection of the beam. No? So if imagine one beam that goes between two beams, you want to check that is L300 or L350, but of its own deformation. No? So you want to discount the deformation that the beam could have at the beginning and the end. You are interested to this delta. So this program is an Excel program that essentially take the data. It's able to understand that the beam goes from one side to the other and is extracting the delta from the total value that SOFiSTiK is giving you. And then you set up a limit. For example, in this case was 300, and this working down on utilization factor and plotting to you for graphs. So you know this beam, for example, is at 90% or 99% or whatever. No? Stop. It's almost finished, huh?
Computer's almost finished. Oh no. Yeah.
Okay. Yeah. Some conclusion. We found some small differences, I would call it, of stiffness between the layer material from SOFiSTiK and the one that, let's say, is theoretically correct. We will investigate why, but for the moment, the results we get from SOFiSTiK are very good. With SOFiPlus, we have a very easy paneling solution that has cut down our time resources for modeling incredible. We can define the joints automatically. That is a huge savings in terms of time. And we have found a way to implement the CLT design procedures into something that we can visually evaluate and also towards the client present in a way that is understandable and not thousands of pages of verification that are useless for presenting your results. We are expecting a new version of the Eurocode 5 where CLT will be included. Will be interesting to see what they say, and also if that the industry will be interested to take this kind of verification into their software, because of course it will be integrated, it will be a better solution. Last but not least, thank you. We are hiring. We are looking for passionate and talented engineers. This is the right place to ask for it, I think. So anyone just can drop me an email, and that's it. I mean, that's the presentation.